Okay, so today I want to talk about cohomology with compact support again. And last time we calculated the cohomology of Rn. And today I want to talk about the technique of the Vietoris sequence for cohomology with compact support. With drum cohomology, the pullback of differential forms induces a mapping cohomology. Okay? However, with compact support, the pullback of a function or a form with compact support doesn't have to have compact support. So the pullback does not induce a mapping cohomology with compact support. And so you need a different theory. You can use proper maps. The pullback of a function with compact support under a proper map has compact support, okay? But we're gonna develop a different theory. So instead of using a pullback, we are gonna use inclusions of open sets, okay? And let me first talk about the extension by zero of a function or of a form, okay? So suppose you have an inclusion of open sets U, okay, in a manifold M, and let I from M to U be the inclusion map. Where U is an open set in M. Okay. Now, if you have a form with compact support in U, say omega, all right. Let's say the support is here. Well, then you can just extend omega by defining it to be zero outside of U. Okay, so you define its extension by zero to be I lower star omega, and that is going to be a form on K. So it is the same as omega for P in U, and is zero outside. And it would still be C infinity, okay? Because obviously on U is C infinity, since on U is the same as omega, but outside of U is zero, okay? And, so there's no problem out here. Now, at the boundary point, because the support of omega is closed, so you have, like you will have a open set that's disjoint from the support, and on that open set, the extension is identically 0, so it's going to be continuous. Okay, yeah. So you see, this is still C infinity. Okay, the extension by 0 is still C infinity, and that's because the support is compact. And let me see. Yeah, right. That is because you have compact support inside U. Okay. If you don't have that, so like, so here's an example. Like, if you have a function, okay, say, say, call this f, and it looks like this. So this, the support is not a, let me see. So yeah. So the support in U is an open set in M, right? Because U is an open set, and this function is not 0 on U. So if the function is not 0 on U, it doesn't have compact support in M, then you cannot extend by 0 to a smooth function. Okay, so if a C infinity form, say omega, does not have compact support, okay, yeah, this is a form that doesn't have compact support, then extension by 0 may not be possible. Okay? Because the extension by 0 would not be C infinity. But if you have compact support, then you can extend the form by 0. Okay. And then if you have two inclusions of open sets, so if, say, J from V to U and I from U into M are both inclusions of open sets, you can compose them. So you can have I composed with J, and okay, and that would be an inclusion of open set also. So you have V included in U, included in M, and you start with something with support, with compact support in V. So you can extend it by 0 to U, then by 0 to M. And so the inclusion by open sets, so the extension by 0 of the composition is the same as you first extend by 0 under J, then you extend by 0 under U. Okay? So you have this property. And of course, the identity map extended by 0 is the identity map. And that says extension by 0 of inclusions of open sets gives you a functor. Right? It gives you a covariant functor. Okay. So, yeah. And, okay. All right. Okay. And now we want to see if it induces a mapping cohomology. So we need to check that it commutes with D. Okay? So inclusions of open sets actually commute with D. And this is easy to show. So I goes from U into M. So we let omega be a form with compact support on U. Okay. Now, let me use this picture here. So we have this picture, and say, now if P is in U, so here's P, P is somewhere in U. If P is in U, because U is open, then there exists an open neighborhood V of E, right? With V in U. Okay. So you have some open neighborhood V in U. And then because V is in U, so on V, the extension is just omega itself. And so if you take the exterior derivative, you get that. But then on V, omega is I star omega, so this is D I star omega. Okay? So if you have a point in U, then the commutativity holds, basically because on a neighborhood, you haven't changed anything. Okay? Now, if P is not in U, if P is not in U, then both sides are zero, right? Because the extension is zero and yeah. Yeah, if P is not in U, then P is not in the support of omega, okay? Because the support of omega is in U. So there exists a neighborhood containing P such that the extension is identically zero on V and omega is identically zero on V. And so both sides are zero. So okay. Yeah. Here? Left-hand side. Oh, right, right. Oh, gosh. Oh, yeah. That's, no, just a minute. I just want to take D of both sides, right? So I take D I star omega, and then here, thank you. So, yeah, D I star omega. And then, so D omega, D omega is on V, right? Uh-huh. No, this is, yeah, no, this is a different picture, right? So here we just have U and V, and M. Now let me see. So on V, yeah. Uh-huh. The, so D omega, D omega has support in U. Yeah, so I mean, this is going to be the same as just I star of D omega. Yeah, right. Because, yeah, D omega, this support of D omega. No, because, so D omega is a form on U. Yeah, so because D omega is a form with compact support in U. Okay. We showed at some point that the exterior derivative is support decreasing. So if omega has compact support in U, so does D omega. And because it's got compact support in U, so like the extension by zero, right, on U is the same as D omega itself. Okay? Yeah, good. All right. So we have shown that I lower star is a co-chain map, and therefore I lower star induces a map in cohomology. So as a co-chain map, I lower star from forms with compact support in U to forms with compact support in M, so induces a map in cohomology that I call I lower hatch. Okay, and so this I lower hatch will be a covariant functor. Okay, and now let's look at the Vietoris sequence with compact support. Okay, so the Vietoris sequence deals with the situation when you have an open cover by two open sets. So my Vietoris. Okay, so let M be the union of two open sets, U, V, open. Then you have quite a few inclusion maps. The intersection can be included in U, and it can be included in V. I'll call the two inclusion maps JU and JV. And then U and V can be included in M, and I call the two inclusion maps IU and IV. So they are going to induce extensions by 0. And now I'm going to define a map from U intersection V to U and V. Okay, so so I want to define this map I lower star from forms with compact support on the intersection to the forms with compact support on U and forms with compact support on V. Okay, so I lower star of oh no, this the first map is J, right? So J lower star. All right. Oh no, no, I don't. Sorry, I'm just gonna call it J. We haven't used the letter J yet. So J, I mean, you can just include in each of them, right? But it's gonna be the signed inclusion. I'm gonna put a sign there. So that means J of omega, okay, is you first extend by 0 from the intersection to U. Okay. And you put a sign there, and then you have the extension by 0 from V intersection to V. Okay. So J is the sign inclusion. And then the next map, and I goes from the direct sum to M, and it is going to be the sum. Okay, so I is going to take a form omega U here, or U, and the form omega V here too. You first extend by 0. Okay. And then you add them. So you see, like, if I is the sum and J is the sign inclusion, then when you compose them, you know, omega will go to 0. Right? Yeah. I composed with J is 0. Okay? You need that to have an exact sequence. So we have defined these two maps, I and J, and then they will give us a short exact sequence. Okay. So, all right. Okay, so here's a theorem. You start with forms with compact support. In the intersection, you go to the direct sum. And then you go to M, the union. Okay. So we have these sequence of maps. And the theorem is that this is exact. Okay. I mean, I already showed that J composed with I is 0. So that means the image of I is in the kernel of J. Exactness at I means that you have an injection. So if you have a map, if you have a form on the intersection, right, and when you look at it, you extend it by 0 to a form on U. If it's 0, then of course the original one is 0. So, I mean, this is easy. Exactness here is it's pretty easy to, and the only part that's a little bit more difficult is here. So exactness at this last term means that J is surjective. And so that means if you are given a form on M, you have to write it as a form, as a sum of a form on U and a form on V. Okay? So let's just check that. Proof. Exactness at the first two terms is easy. Okay, so let's not worry about that. You can check that yourself. And then exactness at omega kc of M is equivalent to surjectivity of J, and J is the sum. So that means given a form omega on M, okay, so need to write it as the sum of a form of omega U on U and omega V on V. How would you do that? This is much easier than the other Vietoris sequence. How do you write? Yeah. Right. Yeah. You choose a partition of unity, rho U and rho V, subordinate to this open cover UV, and then rho U and rho V add up to 1. So that makes it simple. So you choose a C infinity partition of unity, rho U, rho V, subordinate to the open cover UV, and they will add up to 1. And so rho U omega plus rho V omega will add up to omega. And the support of rho U omega, okay, whenever you have a product, the support is contained in the intersection. And so it's contained in the support of rho U. And because rho U is subordinate to the open cover, the support of rho U is in U. Okay? And and then it's also contained in the support of omega. Okay? But you know that the support of omega is compact. And the support of anything is closed. So you have a closed set of a compact set, and therefore it is compact. So rho U omega has compact support contained in U. So thus, rho U omega is a form with compact support in U. And yeah, so you have written omega as the sum of a form with compact support in U and a form with compact support in V. Yeah. So that proves the surjectivity and therefore the exactness at the last term. Okay, and therefore, because now you have a short exact sequence of differential complexes, it induces a long exact sequence in cohomology. And that is going to be the Vietoris sequence with compact support. Okay. So let's see. So the short exact sequence that we have just derived induces a long exact sequence in cohomology. So all right, and so it's going to be HKC from the intersection going to HKC on the sum, and then HKC of M, and then it goes up to HK plus 1C of the intersection. Okay, so these maps I call I lower star and J lower star. Okay. We haven't used these notations before. Have I? No. Yeah. Oh, because these two maps are called I and J. Okay. Yeah. So let's do an example. And I don't want to do a trivial example, you know, like the torus. And so the first non-trivial example is this cohomology with compact support of the Möbius strip. It's also a homework problem. So I'm going to do the homework problem. However, I'm going to change the homework a little bit. So I'm going to do the homework problem one way with a certain orientation. And I'm going to change the homework problem by requiring you to do it in another way using a different orientation. Okay. Yeah. So, yeah. So let's do the homology with compact support of the open Möbius strip. All right, so the open Möbius band looks like this. And this is your M. And you get that by taking a strip. It's open on the top and at the bottom. And you identify the two edges like that, you know, with opposite orientations on the edges. If they have the same orientation, then you just get a cylinder, okay? But if you identify the two edges with opposite orientation, then you get this Möbius strip, okay? Now, we have to know we're going to use this Vietoris sequence, okay? And for the open Möbius strip, okay, so I'm going to choose U, you know, to be like an open rectangle here. So let's say U will be this. This is going to be U. And V will be another open rectangle, okay? That together with U will cover M. So V will be this open rectangle. Okay, so V will go from here to here. Okay, okay, now, let's see. So U is really just What is U? U is just an open rectangle, right? If you glue this edge to this edge, U is just an open rectangle. Okay, so it's diffeomorphic to R2. And V is also an open rectangle, diffeomorphic to R2. And then the intersection consists of two pieces, A and B. So A is another open rectangle and B is another open rectangle. And they're all diffeomorphic to R2. So you know their cohomology with compact support. And you know that the cohomology with compact support is what? Tell me what the cohomology with compact support of R2. That's right. It's got R in dimension in degree 2 and 0 for all other degrees. So in dimension 2, it's R, and you have to know a generator. Because in order to write down these maps, you have to know where the generator goes. What is a generator of H2C of R? Let's see. Like a generator of H2C of R. Okay, so first of all, what kind of object is it? I mean, is it a function? Is it, you know, a vector field? What is it? A generator of H2 has to be a two form, okay? A closed two form, but a two form on M, on R2 will automatically be closed because D of the form will be a three form, and there are no three forms on R2 except 0. So yeah, it has to be a two form with compact support. And how can you make sure that it's not exact? Well, you see, you have compact support. So a compact set in R2 is closed and bounded. So it lies inside a closed circle. And if it's exact, then the integral of omega on R2 will be the integral of d tau, let's say on this disk. And then by Stokes theorem, it's going to be the integral of omega the integral of tau on the boundary of D. But the support of tau is in here. Oh, no, yeah, just a minute. This is, yeah. Well, yeah, the support of tau is is also inside D, okay? Yeah, because, yeah, well, yeah, here, if it is D tall, with tall having compact support in R2, yeah, because it's compact support, you can put, yeah, we can put the support of tall inside some D, okay? So you have a picture like that, and then you see that when you integrate tau on the boundary of D, it's going to be 0 because tau is 0 on the boundary of D. Okay? So if you have an exact form, then its integral will be 0. Therefore, to get a generator, like you need a form that's not exact, a two form that's not exact. Okay? How can you make sure that your two form is not exact? Yeah, just any two form whose integral is not 0 will be a generator. Now, we usually prefer to have integral 1, okay, as a generator. So, so a generator of this H2C is a two form on R2 with compact support, you know, whose integral is 1. Okay? That's a generator. Thus, a generator of H2CR2 is a two form omega with compact support in R2 with integral 1. Okay? And well, how do you picture a two form like that? You know, all you need is like a bump function, you know. If you have a bump function whose volume under the graph is 1, that will give you such a two form. Okay? Yeah. Okay, so you certainly have a very specific formula for a generator. Okay? And now, so let's go back to this picture. Mhm. Yeah. And oh yeah, right. And you see from this that you know you can localize the support, right? You can make the support as small as you like. You know, just make you know this like in this picture. Just yeah, you just make the bump function taller, and you can make the support as small as you like. Okay, so here. Yeah, so we can make the support small. Yes, all right. So I'm going to now I have quite a few cohomology groups here. You know, UV, the intersection, and the intersection has two components, A, B. Yeah. So I'm going to say, yeah, let omega u okay, so be a generator. Maybe I will put a bracket around there. And then be a generator on U, omega V, be a generator on V, okay, etc. Now, in order to integrate, you need an orientation. So we just, we can choose our orientation kind of arbitrarily. Okay, so that's the orientation on U, that's the orientation on V, that's the orientation on A and B. Okay, and so okay, so the orientation on U here will be like this. But what about the orientation here? Is it going to be clockwise or counterclockwise? You have to remember that this edge is the same as this edge, but upside down. Okay, so let me leave that for you to think about during the break. All right. What is the orientation on this part of U? Yeah, because the orientation has to be coherent, right? So like you can't have the orientation counterclockwise at one point and then clockwise at a nearby point. You know. Okay, so let's take a break for 10 minutes and why don't you think about the orientation? Yeah, just tell me what it should be over here. Mhm. Yeah. All right, so let's get started. Um, I actually want to be a little bit more specific about the generator on U, okay? It just has to be a two form whose integral is one. So I don't want a two form that looks like this, okay? So what I want is a two form that integrates to one in the neighborhood of something like this. Okay, so this line will represent like a circle um, minus a point, right? So like, let's see. Okay, yeah. So on U, that will represent let me see. Oh well, no, it's just a straight line, right? Yeah. Okay. Yeah, right. We're not identifying the points on the open boundary. So yeah, it's not a circle. It's just a straight line. Okay, so um, I'm gonna call it S1U. And so I want to choose that generator to integrate to one in small neighborhood of S1U, okay? So be a generator that such that the integral um, on a neighborhood of S1U is 1. Okay? And then for the other open sets, you know, I also have vertical lines. So this one will be S1V, and this here is S1A, and then here I have S1B, okay? Now, actually, this S1A, it is in U. So let me draw it over here. Okay? So S1U, you can choose it to be the same as S1A. And then S1B, okay? So it's here. Yeah, all right. So, let me see. Just a minute. So, I think I was right before, because this part would be this part, right? So yeah. So yeah. S1U equals S1A there. Okay? Yeah. And then so now if I orient U counterclockwise on the left part, what would it have to be on the right part? Would it be counterclockwise or clockwise? Clockwise, yeah. Why? Because this part, well, you can put it over here. Okay? This part you can put over here. And then you see that the orientation, has to be consistent. So the orientation has to go like this. But then you see here, this arrow, it lines up with the arrow on the edge, okay? And this edge is this edge. So this orientation, when you put it over here, it has to line up with the edge, so it has to be like this, okay? So that's the orientation on the right part of U. Mhm. Yeah, okay, so yeah, so now let's see. Let's write down the maps, okay? So we have this generator on H2U, and it's here, okay? Let me see. So and then we have a generator on the intersection. So on the this is HKC of A, direct sum HKC of B, okay? And let's write down the Vietoris sequence for the Möbius strip with this open cover. let me see. Just okay. Yeah. Yeah. So Maya Vietoris for M with compact support. You have the intersection, which is the disjoint union of A and B. And then you have the disjoint union of U and V. And then you have M, okay, which is U union V. And we just need to write down H2, H1, and H0. Okay? So H0, in H0, they're all zero, right? With compact support, because these are all like R2. So you have zero, 0. So this is diffeomorphic to R2, this union R2, and so is this. H0, it's all 0. H1, it's all 0 here and here. Except you don't, oh no, just a minute. Do I know? Oh yeah, right. Yeah. What's H0 of the Möbius strip? What's H0 with compact support of the Möbius strip? This is from homework 1, right? H0 with compact support of a non-compact set is 0, right? Because H0 is represented by constant functions. A constant function on a non-compact set, like the Möbius strip, doesn't have compact support. So this is 0 because M is not compact. Okay, yeah. So I do have 0 here. Okay. But here I don't know, H1 of C. And then H2 of C, I don't know. But I do know that this goes to 0 because there's nothing in H3. Okay, so, and then here, H2 of R2 plus R2, it's R plus R. This is R plus R. And then you have that map. And then you have this map. This is D star. And this is I lower star. This is J lower star. Okay? Yeah, so I cannot write down J lower star because I don't know what H2 of C is. But I should be able to write down I lower star because I know, the generators here. I have omega A and omega B. Okay. Okay, so we need to know like what omega A goes to. Yeah. Okay, so now I lower star is the signed inclusion. Okay? So first I have to figure out what IU lower star of omega A is. Okay? Now omega A, it integrates to 1 in the neighborhood of this line. And yeah, so it, but this line is also in U, and so it also integrates to 1. Oh yeah, so like I have to put an orientation on the line, let's say it goes that way. Okay. So yeah, it gives me 1, um, on A, but the integral is also 1 on U. Okay, so it will go into omega U. Mhm. Okay, and now what is IU low star of omega B? Okay. It integrates to 1 on this line. And if you view it, as part of U, what does the so as part of U, what does it integrate to on U? Yeah. Yeah. Oh, so the thing is that, okay, if you put this piece over here, okay, then, then S1B, right, it actually will go down. Because this one has to be reversed when you put it over there. Okay? But the integral is 1 in this direction. Okay, so in the opposite direction, you'll get -1. So when you put this omega B into U and you integrate, you actually get -1. Okay? So this should be minus omega U. Yeah. And then let's look at IV star of omega A. So now you put A, omega A in V. And what do you think the integral should be when you put omega A, extend by 0 into V and you integrate? I mean, would you get 1 or -1? Notice that omega V, yeah, yeah, it's the blue part, right? So it's oriented this way. Yeah, should it be omega V or the negative? Like, so the question is, do you integrate to 1 or -1 when you integrate omega A here? I mean, look, the orientation is exactly the same as that on U, right? It's consistent. And so so it's going to be the same as just integrating. It's going to be the same as this. Okay, so yeah, you're going to integrate to 1. Okay? And then how about this one? Omega b, and you integrate here. So, okay, so look here then. So omega b, that means it integrates to 1 here. And no, just a minute. Sorry. Yeah, we're looking here, right? In V, just this part. So in that part, yeah, in that part, B has this orientation. Okay? So the orientation on B is the same as the orientation on V. Okay? Right? These two orientations agree. Yeah. So because the two orientations agree, this should be, yeah, you should integrate to 1. So this should be omega V. Yeah, this is a crucial part. Okay? If you get the sign wrong, your answer will be wrong. Okay. And all right, so now that we can write down I lower star. So I lower star okay, so I lower star of omega A, it's the signed inclusion into U and V. So it will be minus IU lower, just a minute. No, gosh. Sorry, I think the first map I called J, right? Yeah. Oh, this is J, and this is I. So what we want to write down is actually J lower star. So these should be J's. Yeah. So J lower star. Okay, so J lower star is the signed inclusion. And so it is going to go into minus omega u, and JB lower star is omega v. It goes there. Okay? And then J lower star of omega b is going to go into the negative of minus omega u, and then this one, omega v. Okay, so it's actually omega u, omega v. And that means J lower star, okay, omega A is 1, 0, will be minus 1, 1. And J lower star of 0, 1 is 1, 1. Okay? So uh, okay. So J lower star of AB should be equal to minus A plus B, okay, minus A plus this, and then A plus B. Okay. Yeah. So that is that map. Therefore, what you know is that it's an isomorphism because this is a non-singular matrix, right? This is minus 1, 1, 1, 1 times AB. So it's got determinant non-zero. J lower star is an isomorphism from R2 to R2. Okay. So what does that say about H1? So H1 of C, H1 with compact support of M, from the exact sequence, you know that it is the kernel uh, let me see. Oh, yeah. So it's the same as the image of the lower star because the lower star is injective. And the image of the lower star is the kernel of J lower star. And that's 0 because J lower star is an isomorphism. Okay, so that's H1 of C. And then what is H2? That's H1C of M. And then H2C of M is what? So you know that H2C of M, by the first isomorphism theorem, H2 of C of M over H2C of M over the, H2C of M is just the image of I lower star. Right. This map is surjective. So it is the image of I lower star. And okay, and the image of a map is this map over its kernel, right? So it is R plus R over the kernel of I lower star. That's the first isomorphism theorem. And the kernel of I lower star is the image of J lower star. Okay, that's by exactness. And the image of J lower star is everything because J lower star is an isomorphism. And so H2C of M is 0. All right. All right. So that's the cohomology with compact support of the open Möbius strip. Okay? And so in this calculation, I have put certain orientations on U, A, and B, and V. In the homework, I'm going to put different orientations on those spaces, and then I ask you to calculate the cohomology with compact support. So you already know the answer, okay? So if you get the answer right, but your map is wrong, you'll get 0. All right, yeah. Because the main thing is to write down the correct map, okay? And that's true, like, for the other problems too, because you can find the cohomology of the real projective plane somewhere on the internet. So if you get the answer right and your work is wrong, you shouldn't get any credit. In the first problem set, I've been grading one of the problems, and a lot of times you write down the Vietoris sequence, but you don't give any explanation. And then you have the correct answer. Now, in that case, you shouldn't get any credit, but because it's the first time, so I only take out like 2 points if your explanation is lacking. But in the future, we're not going to grade the answer, but we're going to grade the work, okay? Okay, so that's it for today. Yeah.